This video demonstrates the operation of a forward and reversed bias diode. The most important operating characteristic of a diode is that it allows current in one direction and blocks current in the opposite direction. When placed in a DC circuit, the diode will either allow or prevent current flow, depending on the polarity of the applied voltage. The two basic operating modes of a diode are forward bias and reverse bias. A forward bias voltage forces the positive and negative current carriers to the junction and collapses the depletion region to allow current flow. A reverse bias voltage widens the depletion region so the diode does not conduct. This diode biasing simulation shows that the diode conducts current to the lamp when the anode is positive with respect to the cathode. In a similar manner, it blocks current to the lamp when the anode is negative with respect to the cathode. This video demonstrates the operation of a single-phase half-wave rectifier circuit. Rectification is the process of changing AC to DC. Because diodes allow current to flow in only one direction, they are used as rectifiers. The AC input is applied to the primary of the transformer. The secondary voltage supplies the rectifier and load resistor. The dual-trace oscilloscope is connected simultaneously, displaying the AC input voltage being applied to the circuit and the resulting DC voltage across the load resistor. During the positive half cycle of the AC input wave, the anode side of the diode is positive. The diode is then forward biased, allowing it to conduct a current to the load. The diode acts as a closed switch during this time. The positive half cycle is developed across the load. During the negative half cycle of the AC input wave, the anode side of the diode is negative. The diode is now reverse biased. As a result, no current can flow through it. The diode acts as an open switch during this time, so no voltage is produced across the load. By viewing the two oscilloscope waveforms, it can be seen that AC voltage to the circuit produces a pulsating DC voltage across the load. This video demonstrates the operation of a single-phase, full-wave bridge rectifier circuit. The half-wave rectifier makes use of only half of the AC input wave. A less pulsating and greater average direct current can be produced by rectifying both half cycles of the AC input wave. The dual-trace oscilloscope is connected to simultaneously display the AC input voltage being applied to the circuit and the resulting DC voltage across the load resistor. Initially, turning on the simulation, you see the input AC waveform displayed on the scope. Upon closing the switch, both the AC input and DC output are displayed. During the positive half cycle, the anodes of D1 and D2 are positive, forward biased, whereas the anodes of D3 and D4 are negative, reverse biased. Electron flow is from the negative side of the line through D1 to the load, then through D2 and back to the other side of the line. During the next half cycle, the polarity of the AC line voltage reverses. As a result, diodes D3 and D4 become forward biased. Electron flow is now from the negative side of the line through D3 to the load, then through D4 and back to the other side of the line. Note that during this half cycle, the current flows through the load in the same direction as before, producing a full wave pulsating direct current. This video demonstrates the operation of a capacitor filter circuit. The pulsations or ripple of the DC voltage can be removed by a filter circuit. Filtering is accomplished by alternately charging and discharging the capacitor. The capacitor is connected through a switch in parallel with the DC output load resistor. With the switch open, the voltage output is half-wave pulsating DC. Under closure of the switch, the capacitor on every positive half cycle of the AC supply charges to the peak value of the AC voltage. On the negative half cycle, the charged capacitor discharges through the load resistor to provide a more constant DC output voltage. The variation in the load voltage, or ripple, is dependent on the value of the capacitor and load. The larger value of the capacitor, the less output voltage ripple. With no capacitor in the circuit, we see just the positive half cycles of the sine wave. Adding the 10 microfarad capacitor smooths out some of the ripple and adding another 20 microfarad capacitor smooths out the ripple even more. This video demonstrates the operation of a three-phase full-wave bridge rectifier circuit. For heavier load demands, such as those required for industrial applications, rectifiers may be supplied from a three-phase AC voltage source. Using three-phase power, it is possible to obtain a low-ripple DC output with very little filtering. For this circuit, 6 diodes are connected in a bridge configuration, similar to the single-phase rectifier bridge to produce the DC output voltage. The cathodes of the upper diode bank connect to the positive DC output bus. The anodes of the lower diode bank connect to the negative DC bus. Each diode conducts in succession while the remaining two are blocking. Each DC output pulse is 60 degrees in duration. The output voltage never drops below a minimum voltage level. This video demonstrates the operation of a Zener diode voltage regulator circuit. Zener diodes are used to provide a fixed reference voltage from a supply voltage that varies. A Zener diode is a type of diode that permits current to flow in the forward direction, like a standard diode, but also in the reverse direction if the voltage is larger than the breakdown voltage, known as the Zener voltage. They are commonly found as part of motor control feedback systems to provide a fixed level of reference voltage for the input and output devices. The input voltage to the reverse bias Zener, or diode circuit, must be higher than that specified Zener voltage. In this simulation of a Zener diode, the maximum input voltage is 12 volts and the regulated rated Zener output voltage is 5.1 volts. The Zener diode is connected in series with the resistor to allow enough reverse bias current to flow for the Zener to operate. Voltage drop across the Zener diode will be equal to the Zener diode's voltage rating. Voltage drop across the series resistor is equal to the difference between the Zener voltage and the input voltage. Note that the Zener diode's voltage remains constant as the input voltage changes within a specified range. This video demonstrates the operation of a bipolar junction transistor current amplification circuit. The transistor is connected to two different DC voltage sources, the supply voltage and the voltage generated by the photovoltaic sensor when exposed to light. These voltage supplies are connected so that the base emitter junction is forward biased and the collector emitter junction is reverse biased. Current in the base lead is called the base current, and current in the collector lead is called the collector current. It is called the common emitter transistor configuration because both the base and collector circuits share the emitter lead as the common connection point. The amount of base current determines the amount of collector current. With no base current, that is, no light shining on the photovoltaic sensor, switch open in this simulation, then there is no collector current, normally off. A small increase in base current generated by the photovoltaic sensor, and in this simulation closing the switch, results in a much larger increase in collector current. Thus, the base current acts to control the amount of collector current. The current amplification factor, or gain, is the ratio of the collector current to the base current. In this case, 100 milliamps divided by 2 milliamps, or a gain of 50. This video demonstrates the operation of a bipolar junction transistor switching of an AC load. When a transistor is used as a switch, it has only two operating states, on and off. Bipolar transistors cannot directly switch AC loads, and they are not usually a good choice for switching higher voltages or currents. In these cases, a relay in conjunction with a low-power transistor is often used. For this application, with the proximity switch open, no base or collector current flows, so the transistor is switched off. The relay coil will be de-energized, and voltage to the load will be switched off by the normally open relay contacts. When the transistor is in the off state, the collector current is almost zero. The voltage drop across the collector and emitter is 12 volts, and the voltage across the relay coil is 0 volts. The proximity sensor switch on closing establishes a small base current that drives the collector fully on to the point where it is said to be saturated, as it cannot pass any more current. The relay coil is energized, and its normally open contacts closed to switch on the AC load. When the transistor is in the on state, collector current is at its maximum value, and the voltage across the collector and emitter drops to near zero, while that across the relay coil increases to approximately 12 volts. Note that the clamping diode is connected in reverse bias across the relay coil and prevents the induced voltage at turnoff from becoming high enough to damage the transistor. This video demonstrates the operation of a Darlington transistor as part of a touch switch circuit. The Darlington transistor is a semiconductor device that combines two bipolar transistors in a single device so that the current amplified by the first transistor is further amplified by the second. The overall current gain is equal to the two individual transistor gains multiplied together. The Darlington pairs are packaged with three legs, like a single transistor. The base of the input transistor, Q1, is connected to one of the electrodes of the touch switch. Placing your finger on the touch plate, in this simulation closing the switch, allows a small amount of current to pass through the skin and establish current flow through the base circuit of Q1 and drive it into saturation. The current amplified by Q1 is amplified further by the output transistor Q2 to switch the LED on. This video demonstrates the operation of a phototransistor optical isolator circuit. When the switch is closed, a low-level DC voltage is applied across the LED of the optical isolator. The light from the LED strikes the phototransistor and switches it into conduction. In this simulation, the status of the switch is communicated as a low-level DC voltage to the logic circuitry. This video demonstrates the operation of a MOSFET off-delay timer circuit. Since the MOSFET gate current flow is negligible, a broad range of time delay periods from minutes to hours is possible. With the switch initially open, the voltage is applied between the drain and the source, but no voltage is applied between the gate and the source. Therefore, no current flows through the MOSFET, and the relay coil will be de-energized. Closing the switch results in a positive voltage being applied to the gate, which triggers the MOSFET into conduction to energize the relay coil and switch the state of its contacts. At the same time, the capacitor charging current charges the capacitor to 12 volts DC. The circuit remains in this state with the relay coil energized as long as the switch remains closed. When the switch is open, the timing action begins. The positive gate circuit to the 24 volt source is opened. The stored positive charge of the capacitor discharges to keep the MOSFET switched on. The capacitor begins to discharge its stored energy through R1 and R2 while still maintaining a positive voltage at the gate. The MOSFET and relay coil continue to conduct a current for as long as it takes the capacitor to discharge. The discharge rate, and thus the off-delay timing period, is adjusted by varying the resistance of R2. Increasing the resistance will slow the rate of discharge and increase the timing period. Decreasing the resistance will have the opposite effect. This video demonstrates the operation of an SCR operated from a DC source. The anode is connected so that it is positive with respect to the cathode, or forward biased. Momentarily closing switch PB1 applies a positive current-limited voltage to the gate of the SCR, which switches the anode to cathode circuit into conduction, thus turning the lamp on. Once the SCR is on, it stays on, even after the gate voltage is removed. The only way to turn the SCR off is to reduce the anode-cathode current to zero by removing the source voltage from the anode-cathode circuit. In this simulation, momentarily opening switch PB2 opens the anode-to-cathode circuit to switch the lamp off. Note that the anode-to-cathode circuit will conduct in just one direction. This occurs only when it is forward biased with the anode positive with respect to the cathode and a positive voltage is applied to the gate. This video demonstrates the operation of an SCR operated from an AC source. The problem of SCR manual turnoff does not occur in AC circuits. This is due to the fact that the SCR is automatically shut off during each half cycle when the AC voltage across the SCR nears zero. As zero voltage is approached, the anode current falls below the holding current value. The SCR stays off throughout the entire negative AC cycle because it is reverse biased. The anode-cathode circuit can be switched on only during the half cycle when the anode is positive or forward biased. With the switch open, no gate current flows, so the anode-cathode circuit remains off at all times. Keeping the switch continuously closed causes the gate, cathode, anode, and cathode circuits to be forward biased at the same time. This results in a half-wave pulsating direct current through the lamp load. Because the SCR is a rectifier, it can conduct only one half of the AC input wave. Therefore, the maximum output delivered to the load is 50%. Its shape is that of a half-wave pulsating DC waveform as viewed on the scope. This video demonstrates the operation of a triac switching circuit. A triac is essentially equivalent to two SCRs joined in reverse parallel with their gates connected together. The result is a bidirectional electronic switch that can be used to provide load current during both halves of an AC supply voltage. A triac may be triggered into conduction by either a positive or negative voltage applied to its gate electrode. Once triggered, the device continues to conduct until the current through it drops below a certain threshold value, such as the end of a half cycle of the alternating current. Maximum output is obtained by utilizing both halfways of the AC input voltage as captured by the scope waveform. The circuit provides random, anywhere in the half cycle fast turn-on of an AC loads. When the switch is closed, a small control current will trigger the triac into conduction. The gate limits the gate current to a small control current value. When the switch is then opened, the triac turns off, when the AC supply voltage and holding current drop to zero or reverse polarity. In this way, large currents can be controlled with a small switch because the switch will have to handle only a small control current needed to turn on the triac. This video demonstrates the operation of a triac switching circuit for a PLC AC output module. The triac is used to switch AC high voltage and current controlling the on-off state of the lamp. The optical isolator separates the output signal of the PLC processor circuit from the field load devices. As part of its normal operation, the processor sets the output on or off according to the logic program. When the processor calls for the lamp to be on, a small voltage is applied across the LED of the optical isolator. The LED emits light, which switches the phototransistor into conduction. This in turn switches the triac into conduction to turn on the lamp. This video demonstrates the operation of an op-amp voltage amplifier circuit. Operational amplifier integrated circuits take the place of amplifiers that formerly required many discrete components. An op-amp is basically a high-gain amplifier that can be used to amplify low-level AC or DC signals. A split-type power supply consisting of a positive supply and an equal and opposite negative supply is used to operate the circuit. The 50K ohm and 500K ohm resistors set the value of the voltage gain of the amplifier. The 50K ohm resistor is called the input resistor, and 500K ohm resistor is called the feedback resistor. The ratio of these two resistance values sets the voltage gain of the amplifier. The scope displays the input green trace and the output red trace waveforms. Note that the output waveform amplitude is 10 times greater than that of the input waveform. This video demonstrates the operation of a two-input logic AND gate. Logic is the ability to make decisions when one or more different factors must be taken into account before an action is taken. A logic gate performs a logical operation on one or more logical inputs and produces a single logical output. With logic gate circuits, there are only two values, 0 and 1. Logically, we can use these two numbers, or we can specify that 0 equal false, or no, or off, or open, or low, and that the 1 is true, yes, on, closed, or high. The logic that applies to an AND gate is that if all inputs are 1, the output will be a 1. If any input is 0, the output will be 0. The hardwired equivalent to this circuit would be two control devices connected in series. This video demonstrates the operation of a two-input logic OR gate. An OR gate produces a 1 output if any of its inputs are 1s. The output is 0 if all the inputs are 0s. The hardwired equivalent to this circuit would be two control devices connected in parallel. This video demonstrates the operation of a NOT gate or inverter. The purpose of a NOT gate or inverter is to make the output state the opposite of the input state. Unlike the AND and OR gate functions, the NOT function can have only one input. If a 1 is applied to the input, a 0 appears at its output. If a 0 is applied to the input, a 1 appears at its output. Because the inverter has only one input, only two input combinations are possible. One hardwired device equivalent to this circuit would be a normally closed, held open door switch. When the door is closed, the switch is open. When the door is open, the switch is closed. This video demonstrates the operation of a NAND gate. A NAND gate is a combination of a NOT gate and an AND gate. It is called a NAND gate after the NOT AND function it performs. Any 0 in the two inputs yields a 1 output. If the two inputs are 1, the output will be 0. This video demonstrates the operation of a NOR gate. A NOR gate is a combination of a NOT gate and an OR gate. It is called a NOR gate after the NOT OR function it performs. The output of a NOR is 1 only if both inputs are 0. Its output is 0 only if no inputs are 1.